Hello, I'm Catherine Peters, Professor of Environmental Engineering at Princeton University.
And I'm Julie Kim, PhD student at Princeton University.
This project is a joint collaboration with the University of Virginia and LaSalle University, and it involves beamline scientists at the Advanced Photon Source. This work is motivated by the need to see spatial patterns of minerals. This is essential for characterizing geological materials in terms of their reactivity, toxicity, porosity, permeability, wettability, strength, and texture. And it is relevant for rocks, mine waste, sediments, and cements. Modern synchrotron X-ray microprobes around the globe have enabled important micro-scale characterizations. And yet, our ability to identify and map minerals on the spatial scales that are relevant in environmental and earth sciences is currently limited by practical considerations of data analysis. Here, we present a machine learning approach for data analysis, which we call smart mineral mapping. Our objective is to generate 2D mineral maps for millimeter-sized areas of rock thin sections. At a leading-edge X-ray microprobe facility, such as the GSE CARS beamline at the APS synchrotron, it is possible to do X-ray diffraction for mineral identification at individual points in a raster scan with micron scale resolution. However, it's not feasible to use the beamline in this way for millimeter-sized areas due to the time needed for XRD data acquisition and interpretation. Our approach is to train a machine learning algorithm using coupled XRF-XRD data, and then solely use XRF data to map minerals at the millimeter scale. The principle behind this is that fluorescence is sensitive to individual elements as well as to local density variations. Therefore, embedded in the XRF data is the information about mineral phases. By training a machine learning algorithm on a data set of coupled XRF-XRD, we are providing a way for the XRF data to reveal what it already knows, mineral identification. This is an important point, as this is not just a statistical application of machine learning, it is one based on physics. For the smart mineral mapper, training of the machine learning algorithm is done using an artificial neural network. The neural network depicted here takes XRF elemental intensities as inputs and predicts mineral identities as outputs. Using the coupled XRF-XRD training data, the neural network learns the relationships between XRF data and mineral abundances. Once trained, the algorithm can be used to interpret new XRF scans to predict mineral abundances without the need for XRD data. The value of this machine learning approach comes from the fact that micro XRF data are relatively fast to collect and interpret, whereas the XRD data take longer to collect and much longer to interpret. This slide shows our work in applying the smart mineral mapping approach to a sample of shale from the Eagle Ford Formation in Texas. The training data came from a scan of 1/4 square millimeter. We allowed for detection of 26 common shale minerals for which there were 8 elements characterized. Application of the resulting trained algorithm on a 14 millimeter squared scan captured many microscale features unique to the stratified texture of this rock. The minerals that were found are the same as those that were found using quantitative powder XRD analyses done on bulk samples. The total time required for this application included the hours for the microfluorescence scan, plus a few seconds for mineral map generation.
To further demonstrate and verify the capabilities of the smart mineral mapper, a formulated mineral mixture of known composition was mapped. We first want to highlight that the 6 minerals identified are in line with the phases added to the mixture, validating our overall approach in characterizing a multi-mineral mixture with overlapping chemistries. And in addition to its use as a verification sample, results demonstrate significant advancements to achieving carbonate and sulfide mineral differentiation. The 3 carbonate minerals in this mixture are characterized by same for calcite and aragonite and similar chemistry for dolomite, but exhibit a wide range of dissolution, precipitation kinetics, and crystal growth characteristics. Similarly, the two sulfide minerals are characterized by its different iron to sulfur ratios and its tendency to interact differently with arsenic under different redox conditions. So for such minerals, there is a clear need for correct labeling of the phases in the context of reactive transport modeling, and the SMART mineral mapper provides significant advancements from currently limited mineral mapping approaches not based on XRD. In this next slide, we present an application sample from a naturally cemented fracture µXRF scan, which was mapped using a previously trained mineral classifier built from two datasets of Eagleford Formation and the mineral mixture. We present the resulting mineral maps from the sample to demonstrate its potential in fracture and pore space segmentation. To do so, an additional thresholding step was introduced to segment what the mineral classifier sees as a quartz or equivalently a blank pixel based on its training data. We refer to a quartz pixel as blank due to its composition made up of only lighter elements. And without the need to generate any new training pixels, we were able to distinguish a truly blank pixel from a pixel composed of quartz, which can be seen on the bottom right figure. So far, we've demonstrated mapping spatial heterogeneity and mineral abundance estimations in multiple natural and synthetic samples, and we would like to conclude by presenting a final application of the SMART mineral mapper to quantify the degree of mineral accessibility. This was done by generating and quantifying mineral adjacency maps, which were drawn by evaluating each pixel for its contacting mineral phase in its adjacent pixels. Such analyses are important not only in better estimating for accessible reactive surface areas, but also important in quantifying the mobilization potential of phases embedded in soluble and reactive phases. In the Eagleford sample analyzed here for demonstration, approximately 28% of the pyrite can be categorized as having high mobilization potential based on its contacting reactive mineral phase calcite.
Thank you for listening, and we'd love to hear from you if you'd like to know more about SMART mineral mapping, or if you have applications that you think are relevant. And check out our entry on Digital Rocks Portal, Project 258, where you can download the data we are working with.